Okay, for number one, we have a football player. He starts off running straight ahead, 35 meters, and then turns to the right, 25 degrees, and runs an additional 15 meters. What the question is asking, what is his final displacement, start to finish, and what direction is he in? Well, we can't use Pythag in this situation because it's not a right triangle. So what we have to do is we have to break both of these vectors into components, x and y, and then add those two together. So to start off, let's call the final displacement d. That's what we're looking for. Then let's call the first vector, vector 1, and the second vector, vector 2. So let's start with vector 1. Since vector 1 is straight in the vertical, it's going upfield, we're only going to have a y component. The x component, right to left, is 0. So v1y equals 35 meters. v1x equals 0 meters. That's an easy one, just like number 7 in question set 3b. So for vector 2, now we have to break it into an x and y component, which is exactly what we did in 3a and 3b. So vector 2y and vector 2x. Let's start off with vector 2y. So that'll be right here. Since our angle is right here, it's 25 degrees, vector y is adjacent. So we're going to use the cosine function. So for right here, cosine 25 degrees equals adjacent, which is vector 2 sub y, over hypotenuse, which is the displacement of vector 2, 15. Let's multiply both sides by 15 to get vector 2 y component by itself. And when we put this in the calculator, we get 13.59 meters. I'm going to put that right up here. Now let's do the same thing for vector 2x component, this part of the triangle right here. For this one, it's the opposite of our angle, so we'll use the sine function. This equals opposite, which is vector 2 component x, divided by hypotenuse, which is our vector 2 displacement, 15. I'll multiply both sides by 15 to get vector 2 sub x by itself, and we get 6.34 meters. So now we have a y component for vector 1 and 2, and an x component for vector 1 and 2. What we're basically doing here is we're taking these two different vectors, we're breaking them down in their components, and then we're making a large Pythag right triangle. So now let's just add these together. So now we're doing final displacement. We're going to do an x component and a final displacement y component. So this final displacement we're breaking into for an x and a y. We just add these two together. So for the x component, 0 plus 6.34 is 6.34 meters. And for d sub y, 35 plus 13.59 is 48.59. Cool? Yep. So now let's do the triangle. We go up 48.59 meters. And we go to the right, 6.34. And let's find the final displacement. Well, to do that, just like we did in question set 3a and 3b, we're going to use Pythag. So 6.34 squared plus 48.59 squared equals c squared. When we add those together, we get 2,401.18. This equals c squared. Let's take the square root of both. And the magnitude of that final displacement vector is 49 meters. So now we have to find the direction. So let's find this angle, theta. Let's see, I'm going to use the inverse of tan. And just a reminder, because we know all three legs of the triangle, the x component 6.34, y component 48.59, and we just found the hypotenuse, we can use any inverse inverse trigonometry function. Sine, cosine, and tangent. I like to mix it up a little bit, keep you guessing. I'm going to use the tangent inverse. And remember that's opposite over adjacent. It's OA on SOHCAHTOA. So now we just plug and chug. We got a tan inverse. Opposite would be 6.34. Adjacent is 48.59. And our final theta equals 7.43 degrees. But keep in mind, because we're starting vertical to the north and we're going to the right, we're going to call this to the right of straight down the field, because that's what we started with in our coordinate plane. It said in the book, it says he starts off running downfield and turns to the right. So we'll say 7.43 degrees to the right of downfield. Or if you change this to a north, south, east, west coordinate, it'd be 7.43 degrees east of north. So let's say right of downfield. Awesome. Oh yeah, this is a fun one. So you have an airplane, takes off from ground level, goes 25 kilometers at a 35-degree angle above the horizontal, above the ground. After those 25 kilometers, they change their angle to 22 degrees above what would be the surface or parallel, and goes an additional 515 kilometers. So the question's asking us, what is the total displacement start to finish? Now keep in mind, guys, I ran out of board space. This would normally, which maybe I'm doing a bad example here, need to be drawn to scale. Okay, so the 25 would need to be about, well, 1/20th the length of 515. But to work out some numbers and stuff and leave us plenty of room, let's just leave it here. So what we got to do is we got to break this down into two vectors. We'll call the first vector vector 1 and the second vector vector 2. And what we're solving for is our final displacement. But bam, we'll call that D. So just like in the last question, let's take vector 1, we'll break it into its x component and y component. Then take vector 2, break it into the x component and y component. Then we'll take vector 1x plus vector 2x, vector 1y plus vector 2y, and we'll come up with the x and y components of our final displacement, and then bam, we'll have the correct answer. I'm going to write a little bit smaller, got quite a bit of writing to do on this one, so well, here it goes. Let's start off with vector 1. We have vector 1 sub x. We also have vector 1 sub y. Well, vector 1 sub x would be right here. Let's see, get another color. Bam, there we go. This would be vector sub x for v1. Okay, so that is actually adjacent to this 35-degree angle. So let's use cosine. So cosine, our angle here is 35, and that equals our adjacent angle, which is vector 1 sub x, divided by the hypotenuse, which is the magnitude, 25. We multiply both sides by 25 to get that to cancel out. And if you plug in your calculator, 25 times cosine of 35, where are we at here? There we go, cool. We get 20.48 kilometers. Wasn't too bad. Let's do the same thing for the y component, which is right here. So now we're going to use sine, right? Because this is opposite our angle. So we'll go sine 35, and this equals opposite v1 sub y over that hypotenuse, 25 kilometers. To get it by itself, let's multiply both sides by 25. And when we plug that in the calculator, 25 times sine of 35, we get, there it is, 14.33 kilometers. So this is exactly what we were doing for 3A and 3B. So we shouldn't have any trouble getting to that point. We do the same thing now for the second vector. Okay? Sometimes these like this is the first vector, so we have v1, and this is the x component, so v1x, v1y. Now we're going to have vector 2 sub x, vector 2 sub y. Those can kind of be intimidating at first, okay? So the more repetitions we get, the better and better you're going to get at it, the more comfortable you're going to become. So just a reminder, when we do v2 sub x, this is our second vector. And the x component will be this right here, right at ground level. So let's knock that out real quick. Our angle is 22 degrees, and this x component is the adjacent leg to this right triangle we're creating. So, we'll use cosine, right? Cosine, 22 degrees, equals adjacent, which is what we're looking for, v2 sub x, over the hypotenuse, which of course is this second vector's magnitude, 515. Multiply both sides by 515. And then we get our answer for vector 2 sub x as 477.50 kilometers. So we took 515 times cosine 22. Now let's do for the y component, which would be this leg right here of our triangle, the vertical component for this vector. Since it's opposite of our angle, we'll use the sine function. Sine of 22 degrees is equal to v2 sub y over 515, the hypotenuse of this triangle. To get the sub y by itself of vector 2, we'll times both sides by 515. That'll cancel. And if you take 515 times sine of 22, we get, looks like 192.92. And that's kilometers, of course. So, initially we had two vectors that we couldn't use Pythag on. We wanted to find what this displacement is, which is right here. I'm going to darken it in for you. That's what we're looking for, this displacement value. So what we've basically done is, we've taken that displacement and we're breaking both vectors into x and y, and now we're going to add them together. So if you can imagine, this is the x component total, this is the y component, and part of this x component, to right here, is from the first vector, and this is from the second vector. The exact same thing going up in the final displacement y vector. This is from vector 1, this is from vector 2. Not drawn to scale, unfortunately. I'm slacking. So let's add them together, right? So final displacement, which is what we're looking for, is d. And you can break d into sub x and sub y, just like we've done here. D sub x would equal, bam, right here, 20.48 plus 477.50. Let's write that down. 20.48 plus 477.5. Let's see if I got that somewhere. I sure do. 479, nope, yep, nope, 497. There we go. 497.98. This is kilometers, mind you. Oh, that's ugly 9. There we go. Same as with d sub y. It equals this one plus this one. And that's going to give us, well, let's write it out. 14.33, yep, plus 192.92. And that gives us a total of 207.25 kilometers. So, what we have to do is, now we have to, I'm going to get some board space here. Now, we're going to take these two components, make a new right triangle, find the final displacement using Pythag. We've been doing that for a minute now. We should be pretty solid at that. And then just use trig, and since we'll know all three legs, you pick the function. We'll use an inverse, and we'll find that angle, or the direction. D sub x is 497, bam, 0.98. D sub y, 207. There's a little better drawn scale. 207.25. So, what is the final displacement? Let's just take Pythag here. 207.25 squared plus 497.98 squared, and I get 290,936.64, and that's equal to c squared. We'll call that displacement squared, same thing. Take that square root of that sucker. The magnitude for our displacement turns out to be 539.38 kilometers. Now let's just find the direction. Okay, so we know the final displacement. If you want to go up to this picture, from here to here is 539.38 kilometers. This is our angle. Let's find out what theta is. I'm going to use, looks like I'm using the sine inverse. Let's take an arrow right here. Sine inverse is equals theta. Remember, sine is so, katoa, so is opposite, 207.